Right now, while you're reading this, roughly 13 billion years of light is finishing a journey it began before Earth existed, before our sun ignited, before any atom in your body was ever assembled inside a dying star. That light is landing on the mirror of the James Webb Space Telescope, and when engineers convert it into an image, they see something that should not be there. Small red points, compact dot-like objects scattered across the young universe. There are thousands of them. And after 4 years of study, 3 peer-reviewed rounds of debate, and dozens of competing theories, NASA has quietly confirmed the uncomfortable truth. They do not know what these things are. They have a name for them informally because you have to call something something. They call them the little red dots. But that name is a placeholder for a mystery so strange that it has forced serious astronomers to propose a category of object that has never existed in physics before. An object that behaves like a star and hides a supermassive black hole inside it, an object that shouldn't be able to form, an object that, if it is real, rewrites the earliest chapters of cosmic history. And here is the part nobody is talking about. The James Webb Space Telescope wasn't hunting for them, it stumbled into them. In the deepest fields it has ever imaged, in patches of sky the size of a grain of sand, held at arm's length, these little red points keep appearing, thousands upon thousands of them, uniformly distributed, matching no known model, emitting no X-rays where X-rays should be pouring out, and existing in numbers that overwhelm every prediction cosmologists have made for the last 30 years. If you follow astronomy at all, you already know that the early universe has been throwing surprises at Webb since the moment it opened its eye. Galaxies too big, too soon, structure that formed too fast, chemistry that appeared too early. But the little red dots are different. They are not too much of a known thing. They are an unknown thing entirely. And the more researchers stare at them, the stranger they become. So stay with me, because what follows is not speculation dressed up as science. This is a real ongoing investigation being conducted right now at institutions like the Space Telescope Science Institute, at Harvard, at the University of Cambridge, at the Max Planck Institute for Astronomy. And what they are finding is quietly one of the most consequential astronomical stories of the decade. To understand why these tiny red points broke astronomy, you have to rewind to the summer of 2022, when Webb had just come online and its infrared instruments were seeing wavelengths of light that no telescope in history had ever collected with this kind of clarity. The first deep survey images arrived. Researchers began sorting through them the way they always have, cataloging galaxies, measuring redshifts, mapping structure, and then, in field after field, in survey after survey, a strange population began to emerge. Not smeared out galaxies, not diffuse clouds of star formation, compact, unresolved points of light. So compact that Webb, even with its extraordinary resolution, could not tell whether they were extended sources at all. They looked like stars in the middle of ancient galaxies, but their light was redshifted so extremely that they were confirmed to be sitting at redshifts of 5, 6, 7, some pushing past 8, which meant the light Webb was catching had left them when the universe was less than 1 billion years old, in some cases less than 700 million, in some cases even earlier, and their spectra were doing something no known population of objects should do. They had the broad emission lines of quasars, the classic fingerprint of hot gas whirling at thousands of kilometers per second around a supermassive black hole. But they were red, deeply red. So red that in optical wavelengths they would be nearly invisible. And they were tiny, so small in the sky that any single one of them, if placed in our neighborhood of the cosmos, would be a rounding error. And the moment the first survey confirmed there were dozens of them in a single tiny sliver of sky, the mystery began. Because dozens in a sliver of sky means millions across the observable universe. It means these things are not exotic edge cases. It means they are common. And common in the early universe, in a form we have never seen before, is not something astronomers can wave away. Now stop and sit with that for a moment. In the first billion years after the Big Bang, in the era when the universe was still forming its first galaxies and lighting up its first stars, there existed a population of compact, deep red, quasar-like objects so numerous that we would expect any deep field to catch them, so uniform in their properties that they look like samples drawn from a single template, and so foreign to our physics that no existing model predicts them, describes them, or accounts for them. And that is only the first piece of the puzzle, because when astronomers looked more carefully at what these objects should be doing, they realized the little red dots were breaking something even more fundamental. Here is why. If a little red dot really does contain a supermassive black hole, the way its broad emission lines suggest, then it should be a quasar, or at least a scaled-down version of one, an active galactic nucleus, an AGN, and AGNs are the loudest objects in the universe. When gas spirals into a supermassive black hole, it heats up to millions of degrees. It emits across the entire electromagnetic spectrum. It emits radio waves and infrared and visible light and ultraviolet. And most importantly, at these temperatures, it emits X-rays, enormous amounts of X-rays. Signatures so bright and so specific that we have used them for decades to identify supermassive black holes across the entire observable universe. NASA's Chandra X-ray Observatory can detect the X-ray glow of a supermassive black hole from billions of light years away. The European XMM Newton Observatory does the same. So when Webb produced its catalog of little red dots, the natural next step was obvious. Point Chandra at them, confirm the black hole, move on. And that is when the mystery deepened. Because when astronomers stacked the Chandra data on hundreds and eventually thousands of little red dots, expecting the collective X-ray signature to glow like a beacon, the result was silence. Not faint X-rays, not obscured X-rays, nothing. Nothing at the sensitivity level where standard obscured quasars still show through. Nothing that fits the model of an AGN reddened by dust. Nothing that matches the expected fingerprint of a supermassive black hole feeding at these masses. And when you have a compact object with the emission lines of a quasar, but none of the X-rays of a quasar, you have a problem. You have an object that is telling you two contradictory things at once. It is telling you a supermassive black hole is at the center, and it is telling you no supermassive black hole is at the center. And here's the twist. It is not a small number of little red dots that show this contradiction. It is essentially all of them. Which means whatever mechanism is silencing the X-rays is a feature of the population, not a fluke. It is built into what these things are. And that means we are not looking at ordinary quasars that happen to be hidden behind a curtain of dust. We are looking at something new. Now, if the X-ray silence were the only surprise, astronomers might still be able to fit these things into a slightly modified version of the standard model. But there is a second, arguably larger problem, and it has to do with sheer unrelenting abundance. Cosmological simulations, which are essentially virtual universes we run inside supercomputers and evolve forward in time using known physics, do a remarkably good job of matching the universe we actually see. They reproduce the distribution of galaxies. They reproduce the growth of large-scale structure. They reproduce the expected number of quasars at every epoch, from a few 100 million years after the Big Bang up to the present. These simulations have been refined for decades. They incorporate general relativity, dark matter, dark energy, the physics of gas cooling, star formation, black hole seeding, and black hole growth. And they make sharp predictions about how many supermassive black holes should exist in the first billion years of the universe. Those predictions are small numbers, rare objects, a handful in a deep field, not thousands. But Webb is finding these little red dots at a rate roughly 100 times higher than any reasonable extrapolation of quasar counts predicts. In some redshift bins, the excess is even worse. And here is why this should matter to you. If there really are that many supermassive black holes crammed into the early universe, we have to explain how they got there. Because a supermassive black hole is not a thing you build overnight. It is a thing that, in the standard picture, takes hundreds of millions of years to grow from a much smaller seed. And even that requires the seed to feed almost continuously at the maximum possible rate the entire time. Nature almost never allows that. And yet, here we are, staring at what look like millions of supermassive black holes already in place before the universe has finished its first birthday. So either our models of how black holes grow are deeply wrong, or these are not the black holes we think they are, or the very earliest universe produced supermassive black holes through a mechanism we have never accounted for. And that is the door through which a truly wild idea walks in. It is worth pausing on how much resistance this idea faced when it was first proposed, because a good astronomer does not reach for the exotic when the ordinary might still fit. For a year, teams tried every conventional explanation they could think of. Maybe the little red dots are dusty starburst galaxies, and the broad emission lines are somehow being faked by rapid winds. Maybe the redness is caused by extreme dust reddening around normal AGN. Maybe the X-ray silence is due to Compton-thick obscuration, so dense that essentially no X-rays escape. Maybe the compactness is an illusion caused by gravitational lensing. Each of these hypotheses was tested. Each of these hypotheses failed to account for all the properties at once. The dust explanation could not reproduce the specific shape of the spectral energy distribution. The starburst explanation could not reproduce the width of the emission lines. The Compton-Thick explanation could not survive the stacked X-ray non-detection at the depth Chandra has reached. And by early 2024, a growing number of researchers began to accept that the puzzle would not yield to any patch of the standard model. Something else was going on, and that is when a paper appeared, then another, and then several more, suggesting that the little red dots might be a genuinely new kind of object. An object that had been sketched out theoretically decades ago, but never before matched to observation. An object with a name so blunt and so evocative that it stopped a lot of people in their tracks. Black hole stars. Now, when you hear that phrase for the first time, your instinct is probably to file it under science fiction. But here's what it actually means, and it is stranger and more elegant than the phrase suggests. Imagine a supermassive black hole, hundreds of thousands or even millions of times the mass of our sun, sitting in the very early universe. In the standard picture, this black hole is naked in the sense that whatever gas is falling into it forms a hot, thin accretion disk that blazes across the electromagnetic spectrum. This is what makes quasars. But now imagine that around this black hole, instead of a thin disk, there is a vast envelope of gas so dense and so extensive that the black hole is essentially cocooned inside it. The energy the black hole releases as it feeds cannot travel freely out into space. It gets absorbed by the surrounding envelope. It heats that envelope from the inside, and the envelope in response glows the way a star glows from its own outer surface, not from the black hole directly. The photosphere you see is the photosphere of an atmosphere kilometers across at least, glowing at a temperature of a few thousand degrees, radiating a spectrum that looks a great deal like a very cool, very red star. Except this is not a star. It is a black hole wearing a star for a coat. It has the outer appearance of a stellar object and the inner engine of a quasar. And it emits no X-rays because the X-rays generated near the black hole are trapped and thermalized by the dense envelope before they can escape. Now stop and sit with that. Because if this idea is right, it means the early universe was populated by things that don't fit either of the two categories we have used for the last 100 years. They are not stars. They are not quasars. They are their own class. And the reason we never saw them before Webb is that no telescope in history had the infrared sensitivity and resolution to catch them. They were hiding in plain sight at wavelengths our previous eyes could not focus. Here is how to picture what a black hole star would look like if you could somehow travel back 13 billion years and stand outside one. You would see something the size of a solar system, maybe larger, glowing a deep, sullen red like an ember at the edge of a fire. From the outside, it would look almost peaceful, a sphere of hot, glowing gas suspended in the darkness of the young cosmos. But underneath that gentle surface would sit a monster, a supermassive black hole, the mass of 1,000,000 or more suns, devouring the envelope from the inside out, converting matter into radiation at a rate that a normal star could not sustain for a millionth of a second. And the envelope would be feeding itself into the black hole while simultaneously being pushed outward by the radiation. The black hole releases, held in a delicate, brutal equilibrium. It would run, in effect, its own internal weather system, its own convection, its own atmospheric physics. It would live for perhaps a few million years, an eye blink in cosmic time, before either the envelope was consumed, blown away, or collapsed further. And then it would fade, either exposing the black hole underneath to reveal it as a naked quasar, or vanishing entirely into a compact remnant that would eventually merge with others to help build the supermassive black holes we see in every galaxy today, including our own. And here's why this should genuinely matter to you. For decades, one of the biggest unresolved questions in astronomy has been what astronomers call the seed problem. When you look at galaxies in the modern universe, almost every large one has a supermassive black hole at its center. Our own galaxy has one. Its mass is about 4 million times the mass of the sun. Other galaxies host black holes billions of times more massive, and every one of them had to grow from something smaller. But what was that something? Was it the collapsed remnant of an early star, a stellar black hole of perhaps 100 solar masses? If so, we cannot mathematically get from that seed to a billion solar mass quasar in the first billion years. There isn't enough time. There isn't enough fuel. There isn't enough anything. So astronomers have proposed heavier seeds, direct collapse black holes, formed from primordial gas clouds that skipped the star phase entirely and collapsed directly into black holes of tens of thousands of solar masses. But those objects have always been theoretical. Nobody had seen one. Nobody had a candidate. And then the little red dots showed up. If they really are black hole stars, if they really contain enormous black holes wrapped in dense envelopes at redshifts approaching the dawn of galaxy formation, then they may be exactly the missing link. They may be the intermediate step between whatever primordial process seeded the earliest black holes and the fully grown quasars we see just a few 100 million years later. They may be the answer to a question we have been asking since the discovery of quasars in the 1960s. And the sheer number of them, that overabundance that broke the models, suddenly starts to make sense. There have to be many of them because most of them will fade or be absorbed into larger structures, and only a small fraction will ever become the giant supermassive black holes at the centers of galaxies. What we are seeing in this reading of the data is the nursery, which brings us to what is happening right now in real time in observatories around the world and above it. Because a hypothesis is not a confirmed discovery, and no one in the astronomical community, at least among those doing the careful work, is claiming that black hole stars are a settled fact. They are the best current explanation for a data set that no other model fits. But that is not the same as proof. And to move from best explanation to confirmed physics, astronomers need to do several things at once. They need higher resolution spectra. Webb's own instruments, particularly NIR SPEC and MIRI, are being pointed at individual little red dots to trace their emission line profiles in detail, checking whether the widths and shapes truly indicate motion near a black hole, or whether they might in some unexpected way be produced by dense stellar winds or other atmospheric physics. They need long baseline monitoring. If these objects contain feeding black holes, their brightness should fluctuate on timescales of months to years, the way quasars fluctuate. If they are more like true stars, they should be steadier. Early monitoring hints at variability, but the data sets are short and the signals are subtle. They need deeper X-ray follow-up. Chandra is aging and its successor concepts are still being planned, but every remaining hour of Chandra time is being fought over. Some of those hours are going to little red dot fields, and they need theoretical progress because a hypothesis is only as strong as the mathematical model behind it, and the black hole star scenario is still being worked out at the level of hydrodynamics and radiative transfer. Papers are appearing in journals like the Astrophysical Journal, in Nature Astronomy, in monthly notices of the Royal Astronomical Society, at a pace that even veterans in the field describe as unusual. It is the sound of a scientific community realizing it may be in the middle of something significant and racing to keep up. And here's the detail that tends to stick with people. Even if it turns out that black hole stars are not the correct explanation, whatever the true nature of the little red dots is, will be, by definition, something we did not know existed. There is no comfortable landing here. There is no ordinary answer waiting behind the curtain. Every path leads somewhere new. Think about what that actually means. We built a telescope, launched it 1,000,000 miles from Earth, unfolded its mirror in the cold dark of the second Lagrange point, and pointed it at slivers of empty sky in the hope that we might learn something about the origins of galaxies. And it came back with an inventory of thousands of objects we cannot classify, not one or two, thousands, enough that they are a population, not a curiosity. Enough that they force us to reconsider what we thought we knew about how the universe assembled itself in its first billion years. And they were there the entire time, sitting in that light for 13 billion years, waiting for us to build an eye sharp enough to see them. There is something almost humbling in that. That the sky, which we have been staring at for as long as there have been eyes on this planet, still holds this much. That an object type we had never imagined could be sitting in the deep field of every constellation, invisible to us not because it is far away, though it is, but because we simply did not have the tools to detect the light it emits. That the universe, which we sometimes flatter ourselves by claiming to understand, is still capable of showing us something entirely new. And there is one more thought worth sitting with as this story continues to unfold. If black hole stars really did exist, they lived and died in the earliest chapter of the universe. Every single one of them is long gone. What we are seeing is a light echo, a message from a period of cosmic history that ended before our galaxy had a shape, before our sun had a place, before any of the stories we tell about ourselves were possible. And yet the material they helped assemble, the black holes they may have grown into, sits at the center of every galaxy we call home. The Milky Way's own supermassive black hole may trace its ancestry, in some sense, to objects exactly like these, which means when you look up at the night sky, at the smear of light that is the plane of our galaxy, you are looking at the descendants of something Webb is only now revealing, something we still do not have a proper name for, something the universe kept hidden until we built the instrument that could catch its glow. Whatever the little red dots turn out to be, they are a reminder that the story of the cosmos is not finished, not the writing of it and not our reading of it. And the next chapter is being drafted right now in observation logs and preprints and spectroscopy runs by people who will spend the coming years trying to answer a question the sky has just asked us. If you found this as strange and wonderful to think about as I did, stick around because I will be following this story as new results come in, and I would love to hear in the comments which part of it landed hardest for you. Was it the silence in the X-rays, the sheer number of them, the idea of a black hole wearing a star as a shell, or the simple quiet fact that 13 billion years of light finally reached a mirror sharp enough to catch it? Whatever it is, share it, subscribe if you want more like this, and stay curious because the sky is not done surprising us yet.